Welcome to Webinar Wednesday from Click to Science Presents. My name is Sandra Frericks, and I will be leading the webinar today. And we are going to be talking about engineering, which is one of my favorite topics to talk about, especially this time of year. I just love summertime engineering activities. There's so many neat things that you can do with youth and, of course, with after-school staff as well. Our focus is going to be on modeling the engineering and design process. And we're going to highlight some resources for training staff from Click to Science PD, and also resources that you can use with youth from NASA and Engineering is Elementary, so that you can use the design process and engineering to help students develop their resources and their skills. And we're going to start with a bit of an icebreaker to give you a chance to think about the engineering design process and what that means. And this comes from the Inventors Using Design Process resource that you can download at the bottom of the page here. And we're going to look at a collection of inventions that I put together. I want you to think about what they are and what we use them for. Share your ideas in the chat box. This is just kind of an icebreaker to get us started and get discussions going. I had a lot of fun doing some research about canning food. Some of you who know my other work, I work with 4-H here in Nebraska, and food preservation is part of the history and legacy of the 4-H program. So it was kind of interesting to explore into this realm just a bit. Canning for the preservation of food, it really goes back to the early 1800s. So there's a lot of history behind that, even though it's the first patent for a can opener didn't appear until 1855. So we identify that these are tools that can be used to open a can of food or other cans or containers. We have a variety of different tools, and they're suited for different purposes. I told you a little bit about what I know about can openers. Do you have anything that you can share in the chat box about what you know about can openers or your own experience with any of these? Alfredo says all devices are meant to open a can, some of which have a specific purpose. Others are improvisations based on which is part of the genius of the design process. Using a screwdriver to open a can works. Using a butcher knife works too. But each of these has a different purpose. Has anybody used the one over on the left that a lot of Boy Scouts or members of the military might carry in their pocket? Have you had experiences with that type of can opener? And has anyone had experiences trying to open a can when they didn't have a can opener? I know I've had that experience when we were on a camp out. We planned everything except the can opener, and we had to look for different ways to solve that problem. What other solutions have you come up with when you had the need to open a can but didn't have a can opener with you? Own experiences. Some different ways we've solved the problem of opening a can without a can opener is using a hammer, a screwdriver, using a bottle. That's interesting. A bottle opener, perhaps, maybe. So looking at the designs here, does anybody know which of these designs for a can opener is the oldest? Before can openers were invented, remember cans were around for about 50 years before can openers were around. So before that, chisels and hammers were the most common tool used. That was how the problem was solved. Oh, I like Michelle's point that cans now come with a pull tab, so you don't necessarily need a can opener. Here's a brief summary of the history of some of these devices so you can get a sense of how can opener designs have changed over time and how the process changed. Sometimes they get smaller, sometimes they get bigger. We saw some industrial can openers on the other side. And as Alfredo pointed out, each of them has a specific purpose. They have an intention. The designer had a particular problem they were trying to solve, and the design they created was the one that they felt had the best potential for solving that particular problem. I think it's really interesting to start with a variety of solutions like this because they're all good solutions to solving the problem of needing to open a can. They all work. Some of them work better than others. Some of them are suited to a particular purpose or a particular need. And when we're working with young people to be inventors and designers, we want them to understand that we're not asking them to come up with the one right answer for what a can opener should look like. There's always room to design a better can opener for a particular purpose or function. And deciding what is the best solution to a very specific problem is really what makes design exciting and fun. Again, one of the things I was very intrigued about in my research was that first can opener that was patented in 1865 didn't come around until there'd been cans in use for quite a while. So someone was the creative person, and I'd have to go back and look at that patent application to see who it was, who realized that there could be a tool that would make this job easier because the job existed before the tool did. And that's really what makes it fun to be a designer, to realize that there's a better solution, a better way of doing things. And it's empowering, and that's how we want to, the youth that we're working with, see engineering and design. This graphic for the engineering design process comes from NASA, and of course if you do a search online you'll find lots of different ways that this process is described, but in general they're similar, and I think this one will give us a good frame for our discussion today of what engineering design is and what are the steps we want to help youth be able to do as they're creating their own solutions. We're going to start by asking a question and identifying what the problem is we're trying to solve. What are we trying to create here? What are some of the constraints we need to understand? We start with the question. The next step is to imagine possible solutions and select one of those perhaps to work on in more detail. That's where the plan comes in. But before we narrow it down, we really want that imagine step to be broad. Lots of different ideas. Remember all the different can openers there were. There's lots of ways to solve the problem, and to narrow in on which one is going to be the best requires us to think broadly first. Then the third part is to come up with a plan to describe, draw our idea, to think about the design, the cost, the materials. That's where planning begins. What would it take to make this idea real? It's often challenging to encourage youth to take the time to plan. We'll also talk, in addition to what needs to be included in the planning stage, how to help construct constraints around how you're leading an activity to encourage youth to be successful in planning. The next step is to create or construct a working model of your idea. Sometimes engineers use computer models or simulations. Sometimes they create scale models to test an idea or put something in a wind cave or something like that to test things out. So there's lots of different ways you can test parts or whole of a solution. But we want to create something, and often when we're working with youth, we try to use inexpensive materials, Legos, cardboard, even paper, to give them a chance to start putting an idea together, to create it and begin to have something physical or something digital that they can evaluate. So it might be that they use a CAD drawing in this first create stage to begin to bring their idea, their plan into reality. The next part is to experiment and test the solution. Does it really work the way we think it's going to? What makes our design or our idea fail? What could we change to make it fail more easily or to make it fail, be less likely to fail? What could we do to make it better, to make it more efficient, to make it less costly, to make it more durable? All of these things can be played with and tinkered around with in that experiment phase where we can start testing it, seeing what happens when we use it, maybe try to make it look better, make it more fun. All of those are the most fun part of the experience for me, playing around with ideas. But we also want to encourage them to take what they learn in the experiment phase to improve or redesign their solution. And as you notice in the model, that brings us back to where we started, asking, is this the solution to the problem we started with? You can always go around this circle many more times to come up with a solution that we're happy with. Sometimes the first trip around the circle may take a day or 2 days, and then you might give them a little bit of time to think about those ideas and come back to them and do the whole process. Again, it really depends on how much time you want to spend playing around with the ideas and the solutions they're building. As we talk about the engineering design process and some of these strategies like testing and evaluating, those are the same strategies, the same processes that we use in the scientific process. But there is a difference between the goals of the scientific process and the goals of the engineering process. When we're doing science, we're looking to create an explanation or a description of how the world works. Science produces information that others can use. Engineers use the information that scientists produce. When we're doing engineering, we're trying to develop solutions to problems or needs. The engineer doesn't necessarily produce information. The engineer produces a thing, a product, or a process. And actually, I think I'm missing a little bit there because most engineers produce a plan for a product or a thing or a process. It's actually usually a technician that puts together the actual product, brings it to market, and then, of course, other people get involved because you need marketing and you need communicators to actually take that idea that the engineer created and turn it into something that consumers can use. So we want to think about engineering and science as related and supporting one another and supporting math as well. But understand that there is a difference. In science, we're looking at how the world works, how we can describe the world, and creating information that is useful for people. In engineering, we're applying that information and creating solutions to the problems that we have in the world. And again, creating ideas and products that are useful for people. So, what do after-school staff need to know and be able to do in order to guide youth through this engineering process and through engineering design challenges? So that the youth can learn to create, so that staff can learn to create experiences for youth that encourage them to use their full creativity and problem-solving skills to think, plan, and create solutions. So again, at Click to Science PD, we really want to focus on what it is that staff know and are able to do So that's what we're going to talk about now, is what do we want our staff to be able to do to provide these experiences for youth in a way that really engage youth and build their skills. The tools we're going to use to do that are from the Click to Science website. And one of the first things we're going to do today is watch a video. And I know we're going to use that video to see this skill in action of working with youth. And as you watch the video, I want you to listen to what the lead engineer does as he's talking with the youth to help them work through the challenge of using design process thinking. Listen to the youth as they ask questions. What do they want to know more about? So we're thinking about design process and how the engineer helps explain that to youth, engage them in it, and why he might be doing that. And then what are the questions that the youth have? What are they asking to know more about? You may want to make some notes to things you're observing during the video, because as I said, this one's a little longer. It's about 3 minutes long. So that when we come back together, you can share some ideas in the chat pod about what you saw in the video and how it helped engage the youth. Let me pull up that.
The challenge for the NASA rover challenge, it's a timed obstacle course and an engineering challenge. For the course, we have to have a rover that will fold up within a 5-foot cube. And they graded this one the #1 design in the world. There were 75 teams in 11 different countries. So they came around and they said, this one is awesome. If I had to take one to the moon right now, this is the one that I would take.
In this video, youth are guided through an engineering challenge with engineers. Watch and listen as the lead engineer encourages the youth to work through the challenge by using a design thinking process that includes questioning, brainstorming, making predictions, testing, and retesting.
They do require us to have non-pneumatic tires. Inflated tires won't work. You take that into space, the volume expands too much and it'll blow up the tires. It won't be any good. So an alternative that we're working for, solving one of the design challenges that have been proposed, is the airless result here. This is a sample of the potential tire that we will be using. You can play with it if you want.
So they have to be strong enough to ride on,
right,
but they have to be weak enough for you to crush.
Exactly.
Can I take this out?
Sure.
What is it?
The little pieces of plastic, it's 3D printed PLA plastic, and so you can print anything you want from the ground up.
That's cool.
Yeah, this is pretty cool. We got some other material. The hardest part about the rover is the design challenge of finding the right kind of wheels. Exactly, because you often have to test a lot. You have to form a lot of prototypes and figure out what material is really going to work and what shape's really going to work.
Which one's really going to work?
You keep testing and keep testing. Once you find something you think is going to be a solution, this one right here, you tweak it just the way you think you need to go to it, and then you test it. You can see the way we kind of went about our design process as far as modeling them. This right here is called a finite element analysis. With this, you can put in what parts of the material are going to be solid in place and they won't be able to move. And you can put in the material types and kind of edit the settings from there.
Which one's worked the best so far?
So far, the one with the plastic. The
Honeycomb one, maybe?
The honeycomb one didn't actually work too well. It was much too rigid. The support was too strong.
So you need to have 4 wheels, or?
We need to have 4 wheels. For testing, we can use just one. We can simulate the weight somehow with 150 pounds. I'm sure we have somebody in here that's 150 pounds, and they can just sit on it, and that'll simulate enough weight.
What was the best material to make it out of? Is it still the rubber so far?
Still the rubber. It's called a 2-part urethane. It's actually, you see it out there, these 2 little jugs, you throw them together and it does something called vulcanize at room temperature. It'll heat itself up and solidify all by itself inside those molds. So that's why now we feel comfortable moving on to the testing phase. We've reached a decision here with the element analysis. We like what we see. So now we're going to test it. If it works great, we'll put those little plastic things in it and make it even better.
Cool.
It is cool, it is cool. We'll actually probably be testing them by Saturday. We'll have a full-scale wheel by Saturday.
I have a question.
Sure. Yeah.
Can you take it outside and let some people drive it?
We can probably take it outside and show you how it's done.
Get where you turn. All right, I'm actually going to do a curve right here.
So what did you notice as we were watching the video about how the engineer interacted with the youth, the questions they had? Share your observations in the chat box. What are the things the engineer talked about? What is your critique of this sort of visit or trip? I've seen some great ideas coming across in the chat box. A lot of emphasis on testing. Both Jen and Annalise noticed that he was talking about testing and tweaking and testing and testing. He talked a lot about constraints too. Those were and that may be partly where they are in the process, but that was really what was the forefront of his mind. But I also agree with Sarah that it helped provide an authentic experience for the youth. He let them handle materials, ask questions, and I'm sure they had a great time getting on the bike as well. Liliana noticed that he used technical language, but he also repeated some of that language in other words so that the kids could understand. So he had a good blend of using technical vocabulary, because that's what scientists do and engineers do, and he wanted them to be familiar with that vocabulary, but also making it relatable. I think that this particular engineer did a good job communicating his work to the youth and helped make it a positive experience for them. What would your next step be for the youth in your program after a visit like this? What would you do next? As you're continuing to share your ideas about what you might do next after a visit like this, I just want to note the conversation that Alfredo and Jen were having in the chat box too, about students really trying to hone in on the one right answer, the best option. Tell me how to do it. And I think that some of the focus on coming up with a single right answer is kind of inherent in how they experience and how they're taught science. And one of the goals I have with an engineering experience is to help open that up, that there isn't always just one best answer, or that you may not have enough information right now to know what the best answer is. There's lots of opportunities for the engineers to talk about the different products that they had tried and the different models, the different ideas that might be the best answer, that they had to try them out before they could decide which was the best answer. And so I think that was a great conversation to hone in on that goal of engineering experiences, to open up ideas so that we're not looking for the one right answer, but we're trying to encourage them to come up with a lot of different answers and evaluate for themselves what the best answer is. Some ideas about what you might do next. Give them a problem to solve. I like that idea. Help them give some input to the engineering team to come up with more ideas. The engineering team isn't done solving this problem, so there's room for the students to have some input. Great ideas there. What we're going to talk about here in the webinar is how we can take an experience like this and connect it to the students doing their own design challenges. And it could be that this actually comes before a field trip. If you have an opportunity to visit some engineers, it might be helpful to have the students do a design challenge first, so they've been through that process and they can talk about it with engineers. And there's some great videos on our website of students who have had design experiences and then take those to an engineering firm and are able to talk with the engineers about circuits and some of the things that they're working on. Or you might follow up a really engaging, fun trip like this one with giving them their own design challenge for things that they could design for on the moon. So the NASA On the Moon Design Challenge, that is a cooperative curriculum effort by Design Squad and NASA, is one of the downloads at the bottom of the page. I do encourage you, if you haven't already downloaded it, to go ahead and download it, because it gives you some great resources you can use with your students to give them a hands-on opportunity to do this work. Other great sources for engineering activities besides NASA and Design Squad, there's SciGirls, and Engineering is Everywhere. And you can find some really good curriculum that you can use with your students. And most of them are free or inexpensive. Now, the materials sometimes do take some cost, but a lot of them are using everyday objects like cardboard and tape and things that you may be able to come up with without too much expense. I happen to like this one, the On the Moon Design Challenges, and I've used all of them, so I feel pretty confident that I can recommend it to you. What we want to talk about is how can we prepare our staff for that center goal of applying a design challenge with youth. And we're going to talk about 3 things that we want the staff to do before they get to applying it with youth. The first one we've already done, and that's see it. And we use the video as a way to see what that looks like. The next thing we want to do with staff is discuss it so they can talk about this engineering design process and what it's like. And then we also would like them to have the opportunity to experience it themselves before they share it with you. So let's move on. We did see it. We watched the video. Now we're going to discuss it. And we're going to think about what you can do as a staff member to help youth be successful in this engineering design process. And just to be clear here, what we're trying to do is model for you an experience you could have with your staff using this recorded webinar, or just using the resources we're presenting here and the Inventors using the engineering design process download. It's a fun training to do because it is hands-on and it's interactive. But how do you get staff to discuss the engineering design process? We're going to take some time to think about how you can facilitate a discussion with your staff and how you can support them in applying what they've discussed with youth. So here's what we're going to have staff do. We want you to think about each step in the engineering design process, and I'll pull up a chat pod in just a second so you can share your ideas about what would help youth be successful in each step. In a face-to-face workshop, you might do this in a discussion at their table, or you might have flip chart paper around the room with each of the steps labeled and give them a chance to go around the room and write some tips about what would help youth be successful at each step in the process. Because we're limited by the webinar process, we have a chat box for you to write some ideas. So this is different. And remember, as we're working with our teams of staff, at this point, we're also trying to encourage them to be open-minded and think about a lot of different things, build on what they already know and they're able to do. So at this stage in the professional development for our staff, we're encouraging them to discuss, to share ideas, and to learn from one another. And we talked about different strategies to do that, sitting around a table, having a discussion if you've got a small group, doing some brainstorming on the wall, whatever really fits your comfort level in facilitating that discussion. The goal here really doesn't have to be that they get the information from you, that you are telling them how to apply or how to lead an engineering design process, but you're helping them think through these steps and think about what they already know and what they can do to encourage youth through each of these steps and giving them an opportunity to learn from one another. I'll give you another minute to finish up what you're typing. Well, probably not a whole minute, but a little bit of time to finish up. And then we'll think about what is the next stage after they've seen a little bit of this skill, they've had a chance to discuss it, then what do we do to help prepare staff for working with youth? We want the staff in our programs to know that they can make a difference in what they do and that they do make the difference in our program. They are the critical element to the success that youth have as they're doing science and engineering. Now, I'll discuss some fundamental experiences we can help provide youth with to help them develop a strong STEM identity. And I want you to see how these are really connected to modeling the science and engineering processes we're talking about today. We can make a difference by getting young people involved in STEM topics and in STEM professions. We can give them opportunities to solve real-world problems like an engineer. That helps support their identity. It also helps them understand this engineering design process or even the scientific process as they're exploring the world around them and trying to describe and explain the world around them. We can support youth by developing their sense of competence and confidence and by providing them with a challenging problem and the opportunity to develop their own solutions. Through engineering, we build their sense of competence and hopefully help them carry that over into other areas of their life. We can help youth see themselves as contributors and participants in the STEM community as they develop and test their ideas and share their ideas with others using the same processes that engineers use to solve real-world problems and helping them connect their problems to the real world around them. So we want them to see that not only do they use technology, not only do they use engineering, but they can develop and create it as well. And we can provide opportunities for them to be part of a team that collaborates together, that struggles and solves problems. By helping teams develop a sense of ownership of their solutions and letting them explore, struggle, and overcome problems on their own, we're building their sense of mastery and ownership of what comes out of that process. By making it their own solution, not your solution, you help them develop an identity as an engineer and as a problem solver. So one of the critical things, I think, as staff are working with youth through the engineering design process is not to come in too quickly to solve problems for them. We don't want to show them the answers or give them solutions, but we want to support them as they struggle through that process on their own. And sometimes that's a bit intimidating, but I think it also helps staff know they don't have to know the answers to guide youth through the process of finding answers. And that's the confidence we want them to get out of the preparation you're giving them before they try to do this with the youth in their program. So the tips and tricks we talked about here come from that Inventors using the design process that you can download in the corner. And it's one of our resources from Click to Science that is designed for staff development and is really easy to use. It focuses on helping staff experience the engineering design process, to remember that their goal is to support youth through that process and to help them understand the skills and knowledge that they already have, bring it into that, and their ability to learn from one another. We're going to give them opportunities to see the skill in action, to talk about it with their peers, and then to apply it with youth. Our goal with these Click to Science webinars is always to help you see how you can use the resources from the website with your own staff. So as we are getting ready to train summer staff, or maybe some of you are already in that process or finishing up that process, does anyone have ideas they want to share in the main chat box about how they're using resources from Click to Science in a creative way? I know the summer program down the street from my house started earlier this week, but I'm also going to go lead a robotics workshop tomorrow for staff that are going to be working with youth this summer. So I know we're right in the midst of that summer training season. So we'd love to have you share your ideas in the chat box about preparing staff to work with students this summer in science and engineering, technology, or math. What are you doing? What have you found to be useful? The other thing I'd like you to share in the chat box before we wrap up today is if there's other resources that you think are really important that the group have for doing great engineering activities with youth. Do you have resources that you're using We mentioned engineering is everywhere and design squad, but are there other things you're using? Jump to robotics from 4-H is one that I think gets a lot of use over the summer. NASA Summer of Innovation themed camps are great opportunities to engage youth in engineering. Do you have any go-to places that you would recommend people find resources